Previously, we'd calculated the inverse of a 2 by 2 matrix. The inverse of a 2 by 2 matrix has this formula. In the denominator in this scaling factor up front was something we called the determinant. And all it was a number, AD minus BC, essentially a product of these diagonal entries. Now, another way that we're going to write it is the following. A inverse will exist only if this determinant of A is non-zero. If we want to figure out whether or not a matrix is invertible, if we don't care about finding the actual entries of the inverse matrix, all we have to do is calculate its determinant. It's a nice little test. So can we generalize this to 3 by 3 or to n by n? You can try to reduce this to the identity, and when you do that, you will end up with some sort of horrible, ugly formula for the determinant. You're going to get another 3 by 3 matrix, and there's going to be this numerical factor in front. So we are going to call this thing the determinant of A again, and it turns out that there is a formula for it in terms of the entries of your original matrix. Now, you can sit there and do the row reduction, but it's a big mess. And just to try to write it out for you, this is what you'll get. It is certainly not as nice as the 2 by 2 result. I do not want you to memorize this. And so you might say, well, this is awful. Why are you writing this out? What I'm going to do is show you a procedure by which you can find this result, and then we can use it to try to generalize to larger matrices. This thing right here, I'm going to write this as A11, and then I'm going to use that determinant notation. It'll be A22, A23, A32, and A33. It's these two things multiplied together, subtract the product of that entry. I will do the same thing for that. We'll have A12, and then we'll have this determinant notation again, A21, A23, A31, A33. And that thing in the green bracket is, again, this product, take away that product. We'll have this final term as another 2 by 2 determinant. A21, A22, A31, A32. And we are calculating this. Each of these things here is called a submatrix of A, and it's a particular submatrix of A. And in a moment, I'm going to tell you how to get it. For the moment, I'm going to write it like this. A11, determinant of the submatrix A11, subtract A12, determinant of this submatrix A12, A13, determinant of this submatrix A13. So if I go back to the original matrix, if you take a look at the thing in the blue, this submatrix I got by taking the entry in front, A11, cross out the row that it lives in, and cross out the column that it lives in. The matrix that I'm left with, A11, is simply that submatrix here. Now, at the same time, the second submatrix, the one in green, I took from taking that entry A12, crossing out the row it lives in, crossing out the column it lives in, and then the remaining submatrix are the remaining entries here, A21, A23, A31, A33. And finally, this one in red, I take the entry, I cross out the row it's in, the column it's in, and then the remaining submatrix is there. Now, there's one last thing that we're going to do. So the signs in front are going to work like this. I'm going to take the subscripts here, 1, 1. 1 refers to the row, and the second entry refers to the column. So I'm going to say it's the determinant of that submatrix A11, and now I'm going to take -1 and raise it to the power of those entries added together. I'm going to turn this into a positive sign, write the value A12, determinant A12, -1 to the power of 1 plus 2, A13, determinant of the submatrix A13, -1 to the power of 1 plus 3. That takes care of the signs that are in front of each. Now, I can refer to this thing here as C11, I can refer to this as C12, and I can refer to this as C13. These things are called cofactors. The determinant of the matrix A is A11 times this cofactor, A12 times this cofactor, and A13 times this cofactor. This is called a cofactor expansion. Now, we chose to start with the top row, and it's going to turn out that it won't matter which row you pick or even which column you pick. You can perform this on any column or row, and you will get the same result. The signs that go in front kind of have this nice checkerboard pattern. You'll get a plus, minus, and that just comes from looking at the powers of -1, and this pattern just kind of goes down like this. This is probably the most gruesome way of calculating a determinant. It generalizes to an n by n matrix. What you do is you replace an n by n determinant with n smaller determinants, n minus 1 times n minus 1 determinants, and it's approximately n factorial steps. Now, n factorial is a number that gets really big really fast, and in fact, for a moderate sized matrix like a 25 by 25 matrix, it would take a computer 500,000 years to compute this. So it ends up being a ton of work. We'll throw this out there as a nice way of doing things for 2 by 2 or 3 by 3 matrices, maybe 4 by 4, but beyond that, it gets really ugly really fast. I'm going to do a cofactor expansion about the first row of the matrix. So the determinant of A, take the first entry of that matrix, A11, block out column 1 and row 1, and the submatrix that I'll be left with is 0, 3, -2, 5. Then, because I'm going in the checkerboard sign pattern, I'll have a plus and then I'll have a minus. So I'll take a negative of the next entry, 1. I'll take that row and that column, I'll cross them out, and then I'll take the next entry of that top row, which is a 6, block out that column, block out that row, and then the submatrix I'm left with is 4, 0, 3, and -2. 8 times 0 minus -6. You have to be really careful here with the signs. Subtract 20 minus 9 plus 6 into -8, subtract 0. 48 minus 11, subtract 48. A -11. Now, if I take that same matrix again, I can do a cofactor expansion on any row or any column, and I'll get the same answer. Now, I haven't proven that result to you, but it turns out to be true. So we're going to do a cofactor expansion about the second column of this matrix. And the reason I'm picking the second column is because it's got some zeros in it. So I really want to exploit the fact that something has zeros. So I will start by going down the column there. I'll get a 1. That has a negative sign in front of it, according to the negative positive checkerboard pattern. If I cross that out and cross that out, I'll get a submatrix here, 4, 3, 3, 5. The next term is a 0, and that's why I picked this column. Subtract -2 into the submatrix there. So I'll cross out that row and I'll cross out that column. I'll get 8, 6, 4, 3. I'll get a -20 minus 9 plus 2 into 24 minus 24, which is a 0. And as advertised, I'll get the same number, -11. A cofactor expansion will always work to get you a determinant, but it gets to be a lot of work. This was a 3 by 3 matrix. If I push it to a 4 by 4 matrix, it's really annoying unless there are a lot of zeros present. So what we're going to do is develop other ways of coming up with the determinant.